Hello, in this video I'd like to talk about this series for pi on 4, which is 1 minus 1/3 plus 1/5 minus 1/7 seventh plus 1/9, etc. It's actually quite amazing why this would be equal to pi on 4, not obvious at all. And what's even more amazing is that this was known to mathematicians in India over 500 years ago. In this video I'd like to talk about how those ancient Indian mathematicians proved that this infinite series actually give us pi on 4. And what they did was to use this arc of a circle. This circle has radius 1, so its circumference, being 2 pi times the radius, would be 2 pi. And we have here is 1/8 of the circumference. So this length here will be pi on 4. And what they did is to prove that this length here is equal to 1 minus 1/3 plus 1/5, etc. By breaking up this arc into lots of little bits. So as an example, let's say we take 5 segments. And if we construct this vertical line here and break that vertical line up into 5 equal length segments, each one would have length 1/5. And what they did is to then look at these lengths of these little red ones. So imagine like straight lines, 5 straight lines to estimate the length of this arc. If we focus in on one of the segments, say this one here, and what they did is to construct 2 right-angled triangles. This red segment goes from this point, perpendicular to this line, and this green segment, which I've labeled Y, goes from this point here, perpendicular to the top line. You want to sit next to me or what? So the good thing about these 2 triangles is they're actually similar. If we notice, they both have a right angle, and both of those 2 triangles share this angle down here. So the fact that those are similar triangles means what we can do is actually get this red length x in terms of this length y. If we look at this red length x divided by the hypotenuse of this triangle, hypotenuse is 1 because it's just the radius of the circle. So x over 1 would be equal to y over the hypotenuse of the longer triangle. Now that one is going to be square root of, this is Pythagoras, 1, if we look at this triangle down here, the hypotenuse will be 1 squared plus this height here, which is 3/5 squared. Okay, so using similar triangles, we have this equation here. But we also have another pair of similar triangles, which is this little triangle here, and then again this big triangle here. Okay, because they share a right angle, and they also share this angle up here. So from that second similar triangle, here you go. So from that second pair of similar triangles, we can have y, which is the base, divided by 1/5, the hypotenuse, is equal to the longer base, which is 1, over the longer hypotenuse, which is now 1 plus 4/5 squared, okay, because this height of this big triangle now is 4/5. Now we can put those 2 equations together. If we imagine getting y by itself, multiplying by 1/5 here, and then subbing all that into this one up here, we'll get x is equal to 1/5 divided by the square root of 1 plus 3/5 squared times the square root of 1 plus 4/5 squared. Not obvious at all yet how this is getting to our infinite series, but what we can do now is put together these 5 lengths, and this is where I probably need to move my head, move my camera. So we'll get, like, these are all very similar. The only difference here is on the denominator, instead of like 3/5 and 4/5, we'll have 0 and 1/5, then 1/5, 2/5, 2/5, 3/5. I've only done 4 there. There's going to be one more, but I just sort of ran out of room. You're doing a great job.
I stopped drawing.
Okay. So we have this expression, which is roughly equal to pi on 4, but I've only used 5 segments here. And what we can do then is take smaller and smaller segments, and in fact, like, let this segment be infinitely small. So we're getting to the same idea as what we do with calculus, which is like, look at infinitely small things. See ya.
Bye, see ya.
See ya. All right, so if we took this 1 on 5, instead of 1 on 5, let's say it's 1 on n, where n is very, very small. We can take that 1 on n out the front. And then see how here on the denominator So if we look at, for example, we had 1 plus 3/5 squared, 1 plus 4/5 squared. As this gets really, really, really small, there's not much difference between 3/5 squared and 4/5 squared. So let's say they're approximately equal. Okay, then this one would just be like approximately 1 plus 4/5 all squared. Then we don't need to worry about the square root because we're timesing that whole thing by itself. So then we have approximately this expression here, 1 over 1 plus 1 on n squared plus 1 over 1 plus 2 on n all squared, etc. Now, when you do learn calculus, you might recognize, okay, this is starting to look like the integral of 1 over 1 plus x squared, which does give us inverse tan. And if we take inverse tan of 1, we know that gives us pi on 4. But we're not using calculus right now, okay? So what the Indian mathematicians did, which was quite clever, obviously, was to recognize that we can write this fraction as an infinite series. Now, if you've never seen that before, it's not at all obvious why that is the case, but it's using this expression here. So if we have 1 over 1 plus x, we can write that as 1 minus x plus x squared minus x cubed plus etc. And you probably learn that when we talk about geometric series, infinite geometric series, or later on again in calculus as a Taylor series. But the Indian mathematicians didn't do any of that. Okay, so this is attributed to this mathematician, Deva. And this is what he did. Break up this fraction. Well, just add x and subtract x on the top. Okay, nothing too clever there. But then we can break up this fraction into 1 plus x over 1 plus x. Well, that's just 1. Okay, so we have 1 minus x times 1 over 1 plus x. Well, that's exactly what we started with. So what we can do then is replace this 1 over 1 plus x with this whole expression here. And we get this like iterating thing. We expand the brackets, we get 1 minus x plus x squared. And you might be able to see where this is going. We can do the same trick again, replace 1 over 1 plus x. And we get 1 minus x plus x squared minus x cubed. And you can see we can keep on doing that again and again forever. And we're going to get to this infinite series here. So how clever is that? All right, so then this is 1 over 1 plus 1 on n squared. So using that expression we just saw, this becomes 1 minus 1 on n all squared plus 1 on n to the power 4 minus 1 on n to the power 6, etc. And we can do a similar thing for those second two terms there and all the subsequent terms in this infinite series. Okay, so we're getting closer now. Probably need one more, I guess, algebraic trick or one more infinite series formula that they knew. If we look at these green terms, these terms are like sums of squares. And the Indians had formulas for sums of squares, sums of cubes, sums of powers of 4, etc. So they actually knew that 1 plus 2 to the k plus 3 to the k plus etc. is approximately equal to n to the k plus 1 divided by k plus 1.
That's ridiculous.
Well, believe it or not, that's what they did. So this is the formula we're looking at. And again, like once you learn calculus, you recognize this as integration. Okay, we add 1 to the power and we divide by the new power. So as k gets larger and larger, this approximation gets better and better. And in calculus, where this is continuous, is actually completely true. But I guess at this stage, what you can do is probably just, check for some small powers. So if I was to say, take the sum of squares of the first 10 integers, it's going to give me 385. It's approximately equal to 10 cubed on 3, which would be like 333. But as I said, like as you take more and more numbers, this approximation gets better and better. All right, so if we accept that one, then we can rewrite these green terms by just taking out the 1 on n squared there. We have exactly 1 squared plus 2 squared plus 3 squared, which we said was approximately n cubed over 3. The blue terms there take out 1 on n to the power 4, and we have 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4, etc., which is n to the power 5 on 5. Same thing again, and you can probably see we're getting very, very close now to our infinite series. Because we actually had a 1 on n out the front of all of these. So whereas I have got n here, 1 on n squared, once I times in the 1 over n, what's going to happen? Is it going to cancel out? Are all the ends going to cancel out?
Yeah.
Yeah, they are. We're going to have 1 minus 1/3 plus 1/5 minus 1/7.
Oh, you rewrited the sum. See?
Is it pretty cool?
Yeah.
Do you want to show yours to the camera?
Do.
To the camera. Hold up to the camera.
You rewrote the sum.
Well done.
You did the sum again, see?
All right, do you want to say, don't forget to subscribe?
Don't forget to subscribe.